Okay, so our next speaker is Yongqiang from Monash University. He's going to tell us about program reduction. Let's welcome the speaker.
Thank you. My name is Yongqiang, and I'm the second author of this paper. Unfortunately, first author cannot come to here because of visa issues, so I will going to introduce this project a little bit briefly. Okay, so this is a joint work between University of Waterloo and Monash University. So let's start from program reduction. Program reduction allows users to specify a certain property that a program has and then remove the property in relevant code in the program. Actually in reality, we use a program that have some specific property, and then we have a checker to check whether we still have this property. And eventually we'll produce a minimized program that can still have this property, but with no other relevant, irrelevant code. So one of the most important applications of program reduction is that compiler debugging. For example, compiler testing technique may generate a program that can trigger the bug in compiler. However, this kind of program, usually they are very, very large, and if we give them to the developers say, hey, I don't know how to process this one. I have thousands of lines of code, what should I do? So to facilitate debugging, we feed this input to the reducer, and then we write a checker. This checker will check whether it triggers this compiler bug. And given them, program reducer can help us to get a minimized program that still triggers this bug, but it's much, much smaller, perhaps that's tens of lines of code. This reduction process is very helpful because debugging a compiler with a much smaller, much simpler code is much easier and more intuitive for the developers. Because of this reason, as shown in these slides, developers from LLVM, GCC, Rust, and many other communities actually encourage users to provide a minimum bug triggering program and after program reduction when you're reporting the bugs. So in this application, the goal of the reducer is to make the output program as small as possible. The reason is that the smaller the program is, the easier developer can quickly understand the reason behind these bugs. However, minimization is not all about program reduction. So another application in program reduction is that to facilitate the bug deduplications. So during the compiler testing process, there can be a large number of bug triggering programs generated, maybe thousands of them. So we cannot directly give all of them to developers because actually many of them trigger the same bug. In other words, they are duplicate bug trigger programs. So to avoid giving maintainers so much redundant work in debugging, we should not only minimize them, these bugs, but also deduplicate these bugs. So a good thing of the program reduction is that after reduction, the difference among these programs can also be reduced. So when two different programs become very similar or even identical after reductions, they are very likely to trigger the same bug, and then developer can easily deduplicate these bugs. So therefore, in program reduction, another desired feature is called canonicalizations. That is, it can reduce the difference among programs trigger the same bugs. Ideally, given a list of programs that trigger the same bug, a perfectly canonicalization reducers can reduce them to a single canonical bug triggering program. But this is just ideal cases. So and it's almost impossible to achieve because of the complexity of programming languages. So what we can do instead is try to increase the level of canonicalizations as much as possible. For example, given such a list of bug triggering programs, we aim to make the reducer produce as few as distinct programs as possible. So this is the best thing we can do. So in summary, there are two goals in program reduction, and one is minimizations, and one is canonicalizations. The first goal has been explored a lot in the last 20 years. And in this work, we want to do more for the second work. So to help the existing language agnostic program reducers to better achieve the canonicalization goals. So language agnostic reduction approach does not leverage language-specific knowledge during the transformations, and it can be applied to a lot of programming languages, no matter it's C++, Java, Rust, JavaScript. They are all applicable in this scenario. So to avoid wasting time on the syntactically invalid program variant, a lot of approaches also use the formal syntax to guide this kind of reductions. So the figure on this slide actually shows the typical workflow of the reducers. So given a current best minimum program, in each iteration, we will produce a variant. So using some program transformations to generate a new variant, and then we check whether it will still have that property. And if yes, we update the current best and do the situation again and again. If otherwise, if it does not have this property, we'll apply a different transformations and generate a new variant. So in this process, the most essential part actually is in the transformations. The transformations actually define the search space and determines the reducer's performance a lot. In previous work, there are two syntactic guided transformations, and one of them is called compatible subtree hoisting. So the idea is that we want to simplify this subtree by hosting a compatible descendants. For example, in this path tree, we can simplify it by replacing it with its subtree, which is also an expression. So such transformation ensures that program after transformation is still a valid program, at least in syntax level. So another transformation is called quantified node reduction, which is referred to the node that corresponds to the production rules whose right hand is non-determined and quantified. For example, in this trace, the statement list actually is a quantified node. Its children can be arbitrary number of statements. And for this node, we can remove some of its children, and it will not bring a syntax. And the idea of this reduction is to simplify the trace by performing data debugging on this kind of list. So these kind of two transformations have been proved that very effective. However, the variant generated by these two transformations are still limited. In other words, only performing these two kind of transformations will make the search space too narrow, and it can have some potential limits in reduction. So to better illustrate this idea, so let's show all these kind of limitations. Let's look at these examples. So let's consider this toy grammar and its path tree. For this path tree, neither of the two transformations can be performed because basically, according to the grammar, the expression cannot be single ID, just based on this grammar. Okay. So substructure hoisting cannot be applied here, and there is no codified node here, so we cannot use the codified node reduction. However, we can still actually propose some new transformations. For example, we can simplify this subtree without breaking its syntax by performing the transformation as shown in figure here. So according to the grammar, expressions can have two forms. The first one is something like a pointer dereference, and the second one is something more like accessing the array elements. So the idea of this kind of transformation is to transfer the expression from one form to a second form. So in this work, we call it as a structure form conversion, and propose to leverage this kind of transformation to improve the reduction performance. But just like other transformations, as FC is very flexible, and applying it to reduction has two main challenges. First, it will significantly impact the search space and make the reduction too inefficient to be feasible. And secondly, a larger portion of the variant generated by SFC can be semantically invalid. And this will losing the property and makes the program inefficient. So our solution to help this is that we can restrict the FC a little bit to make the minimum changes while not converting. When we make the minimum changes to make the when we convert the form, we will try to make sure that we only do the minimum changes. So the insight behind this design is that fewer the changes are made, they are more likely the property can be preserved in the variant. For example, one of the rules that we propose to FSC is that when we do the transformations, we always reuse a subtree, and instead of randomly generating new ones. For example, in the first examples, we reuse the existing identifier instead of generating a new one. So based on FSC, we implement 3 reduction methods, and one is called smaller structure replacement. So this is very straightforward. Basically, you traverse a path tree and replace this subtree with a simpler, easier tree. And the second one is called identifier eliminations. The idea is that given an identifier, if we can eliminate all its usage, we can probably we can remove also structure of its definitions. And now with FSC, we can eliminate the identifier by converting the corresponding structure from one form to another form and do the reductions. So these 2 transformations basically focus on the minimization, and the last one is more focused on the canonicalizations. So the idea behind this method is that given a structure, we can order all the possible forms and do some prioritizations. For example, given a statement, we can prioritize the for statements over the while statement. So this method can potentially reduce the difference among duplicates and benefits bug reductions. Bug deduplications. So in the evaluations, we use 2 benchmarks to evaluate our approach. The first one have around 2,000 C programs that trigger 11 unique crash bugs, and also 1,000 programs that trigger 35 unique missed compilation bugs. And the second benchmark contains 20 C program and 20 Rust program and SMT programs. The first benchmark basically focus on the canonicalization problem, and the second benchmark focus on the reduction problem. So we use 3 baselines, Persis, Vulkan. They are the state-of-art language agnostic reducers, and we also use C reducer as the casual comparison. C reducer use a lot of C-specific transformations to help the reduction. So here is the summary of our evaluations after we integrate the proposed SFC-based reduction in Persis and the Vulkan. We can see that the number of eliminated deduplicates significantly increased around 30 to 40%, and the average size of the program is also significantly decreased from around 10% to 40%. And unfortunately, it brings some overhead, which is kind of inevitable. And if we compare to the results with C reduce, we can see that program agnostic reducers can still not have the same results with the language-specific reducers like C reduce, but at least with FSC, we make this kind of results comparable. So this is basically our work. We introduced the tool of program reduction, and we introduced SFC, the missed pieces, for program reduction and some evaluation results. So at the last, I want to introduce our SFC and its families. SFC and Persis are open source in GitHub. In addition to SFC, we also have Later, which is a template-based language agnostic transformations framework for efficient program reduction, which is going to be published in ASC 25 next month in Korea. And actually, we also have LPR, which published in ESTA 23, the first approach using larger models to help the reduction. We have WDD, CDD, and also Vulkan. And actually, based on this reduction process, we also have proposed a new simple yet very strong baseline for compiler testing with our technique. In 7 different compilers, we found more than 300 compiler bugs. All of them are open source, so feel free to try to use them. And if you have any questions, I will try to answer them. Thank you.
Is there any questions? Okay, while we wait for the audience to come up with a question, I do have a question. So, very interesting talk. Do you think the technique can be generalized to other similar problems like clone detection or like plagiarism detection?
Yeah, I think the clone detection actually, if you have 2 programs have different syntax, maybe use this kind of transformation to help the problem, to help to address this problem. Yeah.